nanohub.org.
All right, so today's lecture, we're going to start discussing these interatomic and intermolecular forces. This is important because it gives rise to the tip sample forces that operate in an atomic force microscope. This discussion is kind of superficial. This discussion, the one I'm going to lead on Thursday, are kind of superficial because you could easily spend a few months on each of these topics, right? This is very complicated business. So I'm not going to go into a lot of the details. I'm going to try to provide an overview. I'll give you some references to the original literature, and you can learn a lot more if you consult those references. In my mind, the best reference is this book by Machiavelli, Intermolecular and Surface Forces. This was pretty much the only readable book in the early 1990s that discussed this material, and I still refer to it an awful lot when I get confused. In your reader, there's this long article by Butt, Capella, and Capel, right? And some of the material that I'm going to talk about is also contained in that, it's about a 100-page review article. So those are two very useful references. What we're basically talking about is what at the atomic length scale determines the force between a tip and, let's say, a substrate. And the answer to that question is basically it's a combination of long-range and short-range electrostatic interactions. Fundamentally, the interaction between the tip and the substrate, fundamentally that's electrostatic in nature. Now, we make a lot of assumptions when we discuss this electrostatic interaction between the tip and the substrate. Okay, one assumption we make is we assume that all the atoms on the tip are the same. We also assume all the atoms in the substrate are the same. In practice, that's not the case. In practice, there could be oxide layers on the tip, there could be oxide layers on the substrate, there could be a water layer coating the tip and the substrate. Right, but the fundamental discussion of the force between the tip and the substrate always assumes that all the atoms are the same, and it assumes that you can add up all the forces between all the atoms in the tip and all the atoms in the substrate. So it basically treats all the atoms, both in the tip and the substrate, as identical, even though some of the atoms on the substrate are in the top layer, and they are clearly different than atoms in the bulk. And clearly there are atoms on the tip apex, which are not as intimately connected to the tip as, let's say, atoms in the bulk of the tip, right? But nonetheless, all those subtleties are glossed over. All the tips atoms are treated the same. All the substrate atoms are treated the same. And we always say these forces that we're going to discuss in the remainder of this lecture, we always say those forces are additive. It's an assumption. Okay. It occurred to me that possibly you haven't recently taken a course in electricity magnetism, right? And if that's the case, then it's probably worthwhile to say a few words about electrostatics and electrostatic forces, right? So the electrostatic force, Coulomb's law, is one of the four fundamental forces in nature. It has a lot of practical applications. In particular, the simplest application of Coulomb's law is if you have 2-point charges, let's say two positive charges. They're located at a point in space. We say there's an electrostatic force between them, given by this force equation. The magnitude of the force is proportional to the product of the charges, Q1 and Q2. The magnitude of the force is inversely proportional to the distance squared. There's a numerical constant, 1/4 pi epsilon naught. That constant is dictated by the units that we use, so that if we measure charges in coulombs, we measure distances in meters, then this constant 1/4 pi epsilon naught is often written as just a constant K, which is 9 times 10 to the 9th newtons meters squared per coulomb squared. Okay, so this force law is, as it's written, assumes that the two charges are in vacuum, right? There's no dielectric medium between the two charges. It also assumes that the charges are stuck, right? So this is a problem that a lot of starting students have. They say, well, this force is going to drive the charges apart, so how can I calculate the force if the charges are in motion? But usually when you calculate Coulomb's law, you're always assuming the charges are somehow stuck down, so this distance between them, r, is well defined, and that's certainly going to be an implicit assumption in everything that we talk about today. We're going to assume that the charges are stuck. We're just going to ask what the force on the charges are. The force is a vector, right? Because it's a vector, it means I can take the same problem, same sequence of charges, right? And I can just change the polarity of the charges and I can get different resultant forces. So the rule is that like charges repel one another, unlike charges attract, and depending on the polarity of the charges Q1, Q2, and Q3 in this diagram, you can get different net force vectors that can be either repulsive, attractive, or they can actually be lateral depending on the polarity of the charges. Okay? So you always have to put in the fact that force is a vector when you do electrostatics. One consequence of the definition of the force in the way that we've defined it is that you can also define an intrinsic property of the charge itself. That intrinsic property of the charge is referred to as the electric field. And so what we say is, we say if there's a positive charge located at some point in space, that positive charge generates an electric field that fills all space. And that electric field has the property that it emanates radially outward from this plus charge. The electric field strength is highest when you're closest to the point charge. The strength of the electric field decreases as you move away from the point charge. And the formal definition of the electric field is that if you put a test charge Q naught in some region of space close to this positive charge, right, that test charge Q naught will feel a force. And this, in the diagram on the left, the force will repel the test charge from the positive field charge. And so the test charge will actually move in the direction of the electric field as I've got drawn. The strength of the electric field is defined as the ratio of the force that test charge feels divided by the charge Q naught. All right, so these are just definitions, things that you need to know in the process of understanding the discussion we're about to have. If you have a negative field charge, the case on the right-hand panel, right? Negative field charges, the electric field lines terminate on the negative charge. So if you put a positive test charge Q naught in the presence of a negative charge, you know opposite charges attract. And in reality, that test charge is going to follow the electric field line and be attracted toward the negative field charge. And again, the strength of the electric field, even the vector quantity of the electric field, is defined as the ratio that test charge Q naught, it's defined as the ratio of the force that test charge Q naught feels divided by the size of that charge Q naught. Right, where Q naught is always assumed to be a positive test charge. So those are electric fields, and we're going to talk about electric fields because anytime you have a distribution of charges, right? Anytime you have a distribution of charges, those charges will generate electric fields that fill all space. And if you have at another point an atom or a molecule that has a charge associated with it, that atom or molecule will experience a force due to the electric field that's generated by this group of charges in some region of space. So you have to know these fundamental definitions about electric fields. Perhaps for the remainder of this talk, the most interesting distribution of charges is the one that I've got sketched on this slide. It's a dipole charge distribution. Dipole charge distribution is nothing more than a negative charge displaced from a positive charge by a distance d. The magnitude of the charges are the same. So minus q, the magnitude of minus q is equal to q, the positive charge. The only difference is the polarity between them. That's the physical dipole, right? You can define something which is very convenient. You can define something called a dipole moment. Dipole moment is defined as this quantity p with a vector sign over it. The vector sign over it comes from the fact that there's an orientation of this dipole moment. The orientation is defined as a vector d that connects the minus charge to the positive charge. So if you imagine a vector going from minus q to plus q, right, and that defines a direction d, then the dipole moment, which is an abstraction, right? It's an abstraction. Right? That dipole moment is the polarity of is the charge q times the vector d. And so I've indicated that in that yellow box. The electric field distribution that results from dipoles is also very well known, right? You've probably seen this even in your high school physics courses. Electric field lines always emanate from positive charges. They always terminate at negative charges. So the distribution of the electric field lines around a physical dipole are indicated by the green arrows in that box. Now, what we'd like to be able to do is, and this is important for the remainder of the lecture, we'd like to be able to characterize these dipole moments in terms of some standard unit, right? And the question is, what standard unit will we use? And so if you go back in the literature historically, right, the standard unit of electrostatic charge is this stat coulomb. It's also called an electrostatic unit in the older literature. And so the definition for a unit dipole moment is going to be 1 stat coulomb of charge separated by 1 angstrom. Right? That's the historical definition that goes back into the early 1900s. And so we define a dipole moment in terms of debye, where 1 debye is defined as this charge q of 1 times 10 to the minus 10 stat coulombs, separated by distance d. D is 1 angstrom. And so the debye technically is defined as 1 times 10 to the minus 18 stat coulombs centimeters. So that gives a problem because nowadays we measure charges in units of coulombs, and we measure distances in units of meters. So if you want to convert 1 debye in this standard set of units that's now kind of antiquated, you have to go through a transformation of units. And at the end of the day, you find out that 1 debye is about 3.33 times 10 to the minus 30 coulomb meters. So when we talk about the dipole moments, that is the standard dipole moment that we're going to be referring to. So 1 debye is this 3.33 times 10 to the minus 30 coulomb meters. So I think the next slide just shows you some typical dipole moments for common solvent molecules. You can find these values in textbooks or on the web. And the point I'm trying to make here is that typical materials that are comprised of hydrocarbons, or in the case of water, it's just water and oxygen, they typically have dipole moments between roughly 0.5 debye and 2 or 3 debye, depending on the polarity of the molecules that are under discussion. And so part of the problem we have is we have to calculate how different dipole moments separated in space, how those dipole moments interact one with another. Because ultimately, the interaction of those dipole moments are going to give rise to interactions between the tip and the substrate. Okay, why do we focus on dipole moments and not free charges? Well, because most of nature is electrically neutral, right? And so we like to believe, at least, that our AFM tip is electrically neutral, which means there are no net positive or negative charges in them. We like to believe that our substrate, to a very good approximation, is electrically neutral. which means there's no net positive or negative charges. And so what you're left with is you're left with these dipole distribution of charges, which are inherent, right? They're inherent in the number of molecules. And what's even more interesting is they can be induced, right? These dipole moments can be physically induced by taking a molecule with no dipole moment, submerging it in an applied electric field. And in the process of putting an electrically neutral molecule in an electric field, you can actually induce a dipole moment. Okay? So this dipole business is going to be important as the lecture wears on. Another important quantity that electrostatics deals with is electrostatic potential energy. Right? And electrostatic potential energy is defined in a similar way to mechanical potential energy. And it basically goes back to the definition of work. Right? If you have a mechanical system and you exert a force over a distance, right? You say you do work on an object. And in the process of doing work on an object, you can also say that you change the mechanical potential energy of that object. And how the potential energy is related to the work is simply, by definition, a minus sign. Okay, so if you calculate the work done, you take the negative value of that, then that's the potential energy that mechanical system might have after you've exerted a certain amount of work on it. And in a similar way, right? In a similar way, you can formulate a definition for work in electrostatics, right? The work in electrostatics is going to be charge that you move times the electric field dotted into the path that you move it, this E dot dl. And likewise, you can define a potential energy capital U of R, where U of R is defined to be negative work that you do. These are formal definitions that you've all struggled with when you took electricity and magnetism in your introductory physics classes. Why is this such a big deal, right? This is such a big deal because forces are vectors. And if you're going to try to calculate the force on something, you have to do the vector sums properly. The potential energy, the electrostatic potential energy, is a scalar quantity. So it's much easier to calculate. And at the end of the day, if you want to calculate what the force on an object is, right, the force on an object is going to be given by a derivative of the electrostatic potential with respect to position. So just like the mechanical potential energy is related to the force by minus a derivative, let's say, with respect to x, if we're just talking about motion in the x direction, so also is the electrostatic force F. It's equal to minus the gradient of this electrostatic potential energy. So the electrostatic potential energy is much easier to calculate than a force, and you can always get the forces from the electrostatic potential energy by taking minus a gradient, minus a derivative, basically. Okay? So that's another important factor. Let's talk a little bit about the form of these electrostatic potential energies, just to remind you what we're talking about. They're really easy to calculate if you have point charges. So for instance, if I have a charge minus Q1, I have a charge plus Q2, they're separated by a distance R1, 2, then the electrostatic potential energy for those two charges is defined to be 1 over 4 pi epsilon naught times Q1 times Q2 divided by their separation distance. Right? Now the trick is you got to put in the polarity of the charges. So if Q1 is negative, you got to put that in. If Q2 is positive, you got to put that in. Net result is that the electrostatic potential energy for that charge distribution is negative, which means there's an attractive force. Right? That means there's an attractive force between the two charges. Right? Negative potential energies mean attractive forces. And likewise, you can do the same calculation for 3 charges, and you can just see how easy it is to do, because it's just the product of the charges divided by the relevant separations. And so you just have to take into account all possible combination of charges. You have to add them up, you have to divide by the separations, and then at the end of the day, you got to put in whether Q1 or Q2 or Q3 is positive or negative. And that number U in the bottom half of this slide could be either positive or negative, depending on where the charges are and what their polarity is. If that number U is a positive number, that means you've got to do work, physical work, to assemble that system of charges. If that number U is a negative number, that means that the charges could, in principle, self-assemble. You could leave them at infinity and bring them in, and you'll actually gain energy in the process of assembling the charges. So this U with a positive and U with a negative value, right? That's going to be also an important concept that will pervade the remainder of this lecture and the lecture on Thursday. Okay? But you have to get the idea that U can be either positive or negative. And the reason is, just depends on where the charges are and what the polarity of the charges are. Okay? How do we connect these definitions of point charges and dipoles to real world situations? Right? And there's a one-to-one analogy, right? Which is not surprising. For instance, point charges if you discuss point charges in real life, those are positive or negative ions that are present in solution or present in the tip or the substrate, right? You can talk about molecules that have permanent dipoles, and those molecules tend to be polar, right? And so you can look up in textbooks what polar molecules are. I list a few of them. These polar molecules, okay, will have permanent dipole moments that can interact one with another through the electrostatic interaction due to dipoles. Okay, one interesting thing is that these polar molecules tend to have bonds between oxygen and hydrogen. They tend to have bonds between carbon and nitrogen, or between hydrogen and fluorine. Right? So these polar molecules tend to have oxygen, fluorine, and nitrogen atoms associated with them. Nonpolar molecules, right, like hexane, benzene, toluene, right, these molecules do not have a permanent dipole moment. Right? There's no oxygen, there's no fluorine, there's no nitrogen in them, right? And they tend to be what we call fluctuating dipoles or induced dipoles. You can induce a dipole moment in those molecules, but only if you subject them to an applied electric field. You know, their very nature, they're nonpolar, okay? And chemists understand these things very well because they can pick the solvent to clean off different types of contaminants based on the polarity of the solvent and the properties of the contamination. There are two other distributions that I just mentioned, right? You can have a surface charge distribution sigma. That occurs if you take let's say a metal plate and you charge it up with a battery. If you just put a battery on a metal plate, that plate will charge up. There'll be a surface charge density sigma in coulombs per meter squared. And then lastly, you can have a volume charge distribution rho, which is coulombs per cubic meter. So you can imagine taking a ball of styrofoam and injecting charges in it, right? The distribution of charges in that ball is described by this charge distribution rho. Okay, so what we want to do is we want to take these basic facts of electrostatics and we want to apply them to the problem of interatomic and intermolecular forces. And in particular, these interatomic and intermolecular forces are going to range over a few picometers, so they're going to be very short range, okay? Or they could be very long range, up to nanometers in size. So there's about a factor of 1,000 in the length scale that these electrostatic forces interact. And the electrostatic forces can be split into roughly 3 different categories. Right? If you sit down and think about this for a long time, or if you read Machiavelli's book, right, you quickly come to the realization that these electrostatic forces can be described in terms of straight electrostatic forces. These are the forces between ions and permanent dipoles, one with respect to another. Right? So that's the first one, just straight electrostatic forces. There's something called polarization forces, which means that if you take a nonpolar molecule and you put it in an electric field, normally you wouldn't expect any interaction, but the electric field polarizes the molecule. Okay, we're going to have to calculate that. We're going to have to estimate it. Once the molecule is polarized, it has a dipole moment. That dipole moment can interact with the electric field, right? And then it becomes very important to know how that dipole is oriented with respect to the applied electric field. There's an energetics calculation that's involved. So that's referred to as polarization forces. And then lastly, we have these dispersion forces, right? The dispersion forces are fundamentally electrodynamic in nature, and they are forces between fluctuating dipoles separated in space by many hundreds of nanometers, right? And you wouldn't think there would be a net electrostatic repulsive or attractive interaction between dipoles that just fluctuate in time and space, but we'll show you there actually is. And it's one of the dominant forces that describe how the tip interacts with the substrate. So it's a pretty subtle effect. It's not the sort of thing you learn about when you take your first course in electrostatics, okay? There are two other forces. One is the covalent bond force. That's the force that's very familiar to chemists. That describes if there's a chemical bonding between two different atoms. And lastly, we have this, what's known as a polyrepulsion force, right? That means if you try to bring two atoms close enough, one against another, they start to feel a strong repulsive interaction. Those two forces are quantum in origin, and we will not discuss them in great detail, not nearly as much detail as the Coulombic forces, which are primarily electrostatic. Okay? So, that's the plan, right? For the rest of today, I'm going to try to skip through the first three categories of forces and describe a little bit about what's known regarding them. Before I do that, I have to say something about how two atoms interact. Okay? How do two atoms interact? And there's a very simple formula that describes this interaction, electrostatic interaction. It's given by what's known as a 612 or a Leonard-Jones interatomic potential. Right? It contains two terms. The term that's negative, the sigma over r to the sixth, that describes, to a first approximation, these dispersion forces that interact between two atoms as they're brought closer one to another. Turns out the dispersion forces are going to give rise to a characteristic 1 over r to the sixth behavior. So you'll see that over and over again. The sigma over r to the 12th factor, that describes this Pauli exclusion force. So when you try to bring two atoms very close to one another, there's an extremely strong repulsive force between the two of them. And that's described by the sigma over r to the 12th term. That is empirical, right? The 1 over r to the sixth is something that we'll discuss, and we can justify the 1 over r to the sixth behavior. There are two important parameters in that interaction equation. One is the parameter U naught. U naught turns out to describe the depth of the potential that the two atoms interact with. So if I just plot that function on the bottom part of the graph, I get the dashed line where U is given by the black dashed line. It has a characteristic depth associated with it. You can see there's a characteristic minimum, and in this plot it's about maybe 0.38 nanometers. And then after you reach that minimum in the interaction potential, there's a very sharp, steep rise, right? That very sharp, steep rise is due to that sigma over r to the 12th behavior. And what it means that if you bring two atoms together, interacting through this Leonard-Jones potential, right, the two atoms will tend to settle at a separation distance that's given by a minimum in U, right? So the bottom of that well is, all things being equal, the bottom of that well is where the two atoms would like to reside, right? The separation between them, there would be one atom at z equal to 0, another atom at 0.38 nanometers, and they would rest there. Okay? The depth of the well is controlled by this parameter U naught. The position of the minimum is, in a sense, controlled by that parameter sigma. Right? Because when sigma is equal to R, then term in the square brackets cancels. That means U is equal to 0. And so the value of sigma, where U crosses the axis there between negative and positive, that's the measure of U. That's the measure of sigma. The thing you got to realize is that once you've got this interatomic potential, you can always find the force between the two atoms by taking a negative derivative of that potential with respect to R, right? That's the way electrostatics is set up. So if I take the derivative of U with respect to R, I get the force, and the force is indicated by the red line. Okay? Okay, now what you'll notice is that the force has a zero. The force is zero at exactly the same position where the electrostatic potential is a minimum. Right? So you see that circle around F equals 0 there. If you drop down, you'll find that coincides precisely with the minimum in the potential well. So you have to get used to going back and forth between forces and potentials. And the way to do it is to keep this in mind. This is the case for two atoms interacting, one with respect to another, by this Leonard-Jones model. Okay? We'll come back to this many times throughout the semester. Okay? And here I just try to make the case a little bit more explicitly. Given that model, you can work out exact values of the location, for instance, of the crossing of U at 0. That's defined by sigma. There's a parameter R star, which is the minimum in U. And because it's a 612 potential, you can work out exactly what that is in terms of sigma. And then you can also find out the position where the force is a maximum. And you can also evaluate that because it's a 612 potential. Right? You can evaluate that in terms of sigma. It's often conventional to take this parameter 4U naught, sigma raised to the 6th power. It's often conventional to replace that by some constant C, right? And so very often you're going to write the attractive force between two objects, two molecules, is going to go as C over R to the 6th with a negative sign. Okay? And experimentally, that parameter C is a number that you have to back out from experiment. In some instances, there are detailed calculations that tell you what that parameter C is. I just worked through a couple of typical values, right? Typically, U naught is on the order of, let's say, half an electron volt deep. Typically, sigma is on the order of 0.25 nanometers. If you evaluate C, you get this funny number, 8 times 10 to the minus 77 joules meters to the 6th. Okay? And so the numbers that we're going to find that reside in the numerator of this U of R potential, they're going to be numbers that are going to be 10 to the minus a big number in terms of joules meters to the 6th power, right? So you have to keep that in mind because we're going to be showing you calculations of C from first principles as this lecture evolves. So I want to get you used to what that number means, and these are just typical values for the numbers. So if you understand all that, okay, now we're ready to jump into what are the forces that act between atoms in a tip and atoms in a substrate. And these forces can be categorized into seven categories, right? And we'll go through some of these very quickly. The important thing is to keep track of the R dependence of these interactions, right? Because the R dependence of these interactions are going to become important when we calculate the forces by taking negative derivative of U with respect to the appropriate separation variable. Okay, so we'll start off with the first first case, the ion-ion interactions, those are the simplest to understand, and then we'll work our way through down to the dispersion interactions, which are quantum mechanical in nature, and I'll just summarize the result. There's a question.
Yeah, no, I was just wondering, when you compare this with STM, in STM, pretty much the tunneling current, you see it clearly as a connection to linear density, the density of states, basically. Whereas as soon as we go to AFM, we've got now this very diverse variety of interactions that lead to, and so the interpretation of forces. And it's just a comment, I think, that it's certainly very diverse compared to STM, it seems to be.
Yeah, so the question is, why didn't we talk about all these forces when we discussed STM? And a lot of the one answer to that question is the separation between the tip and the substrate, right? For STM, the separation between the tip and the substrate is on the order of 0.6, 0.7 nanometers, maybe higher, right? And at those separations, these forces are reduced, right? When you're talking about AFM, separation between the tip and the substrate is literally atomic dimensions. 0.2, 0.3 nanometers, right? And it turns out the last three forces here, the polarization force, the dipole-induced dipole interaction, and the dispersion interaction, those all tend to have a range that dominates in that 0.3 to 0.6, 0.7 nanometer range. So one reason I think STM doesn't deal with it too much is because the tip tends to be a little further away from the substrate than in the case of AFMs.
And I was just also referring to the fact that, there if you measure tunneling current versus voltage, the interpretation of what you see is, LDOS. And when you look at this, you might measure forces, the interpretation of it, but it depends on, all these very different kind of interactions, each with its own laws, so it just seems much more complicated in some sense than STM.
Yeah, well, AFM is not simple, right? If you really want to understand what you're doing with AFM, you have to worry about a lot of things. There's another question?
Well, yeah, I was just wondering, what is the difference between dipole-dipole interactions and dipole-induced dipole interactions?
We'll talk about that. So dipole-dipole interactions would be they already have dipoles. Right? Dipole-induced dipole would mean one has a dipole, the other doesn't, but the electric field from this molecule induces a dipole here, and then they can interact. Okay? Question? Great. So this is the plan, right? I have about 40 minutes to cover 7 different forces. Start with the simplest one first, right? The ion-ion force is just a straightforward application of Coulomb's law, right? We've already discussed this, right? And in particular, the magnitude of the Coulomb force is a 1 over r squared force. Depends on the product of Q1 and Q2. The interaction potential, the interaction electrostatic potential energy is this U of R, and it's only proportional to 1 over R, right? So it's related to the force by the derivative of U with respect to R, but it's got a 1 over R dependence, not a 1 over R squared dependence. And it's important for you to realize that, right? So anytime you might measure a potential energy, when electrostatics are involved and that potential energy scales as 1 over the distance between two objects, that would be a signature of ion-ion interactions. Now, technically, Coulomb's law is only applicable in a vacuum, right? And the question is, if the charges are now submerged in a material that's not a vacuum, how do we handle that? And the answer is pretty simple. Everywhere you see epsilon naught, you basically replace it by epsilon times epsilon naught. Epsilon is a dielectric constant that characterizes the medium that surrounds the two charges. right? So you can imagine taking these two charges, for instance, and submerging them in a bucket of benzene or something. And then you can ask, how is the force between the two charges altered? Well, the answer is you have to find out what the dielectric constant of benzene is. It's a number. You can look it up. You make the substitution everywhere you see epsilon naught, you substitute epsilon times epsilon naught. Okay? So the forces are reduced. The forces are always reduced if you submerge these charges in an insulating material. Okay? So that's simple. Right? The next case to worry about is how, let's say, a permanent dipole interacts, right? And so the question is, how might you form a permanent dipole? And for some reason, you can have, let's say, an electrically neutral atom or molecule that's indicated schematically in this diagram. And in the process of assembling that molecule, there could be various forces, could be geometric in nature, but for whatever reason, there's a separation of charges. So negative charges are at one end, positive charges are at the other. And whenever that happens, we then replace that molecule in terms of an electrostatic model by this dipole. It's an equivalent electrical dipole. Right? The net charge on the dipole is 0. It's just that the charges are now separated by this distance d. And so you might imagine, right? You might imagine that if you're far away from that dipole and you look at it, it appears to you as if there's no net charge. Because typically d is a small number on the order of a fraction of a nanometer. Right? So if you're meters away, right? That small separation would not be discernible, and you would say to a first approximation, oh, the thing is electrically neutral. But as you start to approach the dipole, right, and when, in particular, when you start to get to distances comparable to the separation between those charges, then everything changes, right? You actually see that charge separation, and you have to start taking into account the forces that are exerted on the charges, okay? So I try to make that case in this diagram, which is just a real simple picture, right? It shows a permanent dipole, plus Q minus Q. It's located at a certain distance away from a point charge. So the point charge has a charge on it, let's say, plus Q. And the question is, would there be any interaction between that positive charge plus Q and the two charges, little plus Q and small minus Q associated with that dipole? And the answer is, yeah, there's going to be an interaction because, right, you can apply Coulomb's law, right? You can apply Coulomb's law pairwise between all the charges involved, right? So the plus Q will interact with the plus capital Q will interact with the charge small plus Q, and since those are like charges, there'll be a repulsive force. That repulsive force will be radial, so you have to draw a line between plus Q and little plus Q, and there will be a force that acts, a Coulombic force that acts to repel the positive charge from the point charge plus Q. Likewise, there'll be an attractive force on the little charge minus Q. Right? And so there'll tend to be a torque on that dipole if that dipole is fixed. If it's pinned at the center of the dipole because of these forces, right, the dipole will try to reorient itself. Right? It'll try to twist. What is the interaction potential? What is the potential energy that describes this situation? Well, if I know what the dipole moment of my dipole is, P, if I know what that is, and if I know what my point charge plus Q is, right, the interaction energy, U, is minus QP times the cosine of theta, right, where theta is defined by that angle, divided by 1 over R squared, 1 over R squared, not 1 over R, times this 4 pi epsilon epsilon naught. So if this whole system is immersed in a dielectric bath, you have to tell me what epsilon, the dielectric constant, is. This tells me what the interaction energy is for that very simple system. Okay? So point charge and a dipole interact is 1 over r squared. So that's the next simplest case. After you do the ion-ion, then you go ion-dipole. That's the next case to consider. Third case to consider would be the dipole-dipole interaction. So this is the case where you've actually got two dipoles separated by some distance r. Okay? And this already starts to get complicated because you've got 4 variables you've got to take into account. You've got to take into account the separation between the dipoles. Dipole 1 could be oriented at an angle theta 1. Dipole 2 could be oriented at an arbitrary angle theta 2. And then there's also the possibility that there could be a twist between dipole 1 and dipole 2, and that twist angle is referred to as the angle phi. Right? So you already have to take into account the distance plus 3 angles if you want to calculate the interaction energy for this system. And you can sit down and calculate the interaction energy for the system, and the answer is given at the bottom of the slide. It involves these angles theta 1, theta 2, and phi. Right? Again, you've got the standard 4 pi epsilon naught factor that always is present. Right? This interaction energy is 1 over r cubed. Right? So you got to keep track of these things. If it's point charge, the interaction energy varies as 1 over r. If it's point charge dipole, it varies as 1 over r squared. If it's dipole, it's 1 over r cubed. So every time you reduce the net charge in the system, right, you're basically reducing the r dependence, right? You're making it much shorter range. Okay, so 1 over r is a long range interaction. 1 over r cubed is a shorter range interaction. Okay? So to try to emphasize that, you can do some simple model calculations. Right? I tried to run through one here, right? I pretended I had 2 identical dipoles. The dipole on the right is fixed in the orientation that I've got drawn. The dipole on the left is free to rotate. Right? And I just calculate the interaction energy between these dipoles as a function of that rotation angle. And I do that in such a way that I vary the spacing between the dipoles. So I imagine a hypothetical sphere, right? Diameter of the sphere is S. The dipole is embedded in the center of that sphere. The dipole separation is D. And so I can do the calculation for different ratios of D over S, right? So as D gets close to S, so as the ratio of D over S gets to be 1, the dipoles are very, very close to one another. As D over S gets smaller, right, it basically means the dipole is shrinking, the separation between the dipoles is increasing. And if you just do the calculation for this interaction potential, right, as a function of angle, what you'll find that there's a very sharp minimum in the interaction potential when the dipoles are very close to one another. That's indicated by that red curve, right? But as you physically move the dipoles further apart, right, you'll end up with a curve which is labeled in, it's the black dashed line, let's say. This is for a separation, a ratio of D over S equal to 0.3. So that very sharp minimum that was present when the dipoles are very close to one another, that disappears as you move the dipoles further apart. Right? Now this is important because, right, systems always try to go to their lowest energy state. Right? And the question is lowest energy state with respect to what? And the answer is with respect to KT, because all these systems we're talking about are in thermal equilibrium. At least we're assuming they're in thermal equilibrium. So thermal energies are on the order of KT, right? That's a fundamental principle of statistical physics. And so the depth of this well compared to these thermal energies KT is going to determine what orientation, for instance, these dipoles might have if they're free to move around a little bit due to the thermal energy present in the system. Okay? So I want to illustrate that very simply and get you to start thinking about KT in the next slide. Right? I do two simple calculations. Right? So first of all, we have to talk a little bit about KT. Right? When we say KT, we're referring to the product Boltzmann's constant. Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin. Right? When we multiply that by the temperature T in degrees Kelvin, right, we get a thermal energy, a characteristic thermal energy that's available to all the atoms, all the molecules in the system. So for instance, if I pick room temperature, which happens to be close to 300 Kelvin, then the product of KT turns out, you can do the arithmetic, it turns out to be about 4 times 10 to the minus 21 joules. It's a small energy, right? It's a small energy. And so if the interaction energy between these dipoles is comparable to that KT, right, then these dipoles can move around. They can start to fluctuate. If the interaction energy is much greater than KT, that means that the dipole moments could be locked, and the thermal energy, at least at room temperature, the thermal energy would not be enough to cause them to vibrate or rotate one with respect to another. Right? So I never can remember 4.1 times 10 to the minus 21 joules. But I can remember 4.1 piconewtons acting over a nanometer. Right? So if you want to convert KT in energies in joules to forces in nanometers, I always remember KT at room temperature is equivalent, roughly equivalent to 4 piconewtons acting over a distance of a nanometer. They're equivalent. For some reason, I can always remember 4 piconewtons acting over a nanometer. So I don't have to always calculate KT. I just remember that number. Okay? So if an electrostatic interaction is strong, right? If an electrostatic interaction is strong, these interaction energies U are going to be hundreds of KT, right? Which means that thermal energies at room temperature are not going to cause the system to fluctuate or fly apart. So to just do a simple example, right? You can calculate two charges, two electron charges separated a distance of 0.276 nanometers. This turns out to be the equilibrium separation between a sodium ion and a chlorine ion in sodium chloride. And so if you just calculate what the electrostatic interaction energy for those two things are, it's simple, right? It's a 1 over R interaction because we're dealing with point charges, 1 over 4 pi epsilon naught because we're pretending we're in vacuum, right? Q1 and Q2 are just the electron charges, and you work out the calculation, you find out that that interaction energy is negative, which means that the interaction is favored, and it's about 8.3 times 10 to the minus 19 joules, which in terms of KT is about 200 KT, right? So that would be a very strong interaction, right? Electrostatic interaction. And so you would expect that a sodium and a chlorine atom would be happy to be 0.276 nanometers apart from one another at room temperature, right? And of course it is, right? Sodium chloride is stable at room temperature. That's a strong electrostatic interaction. An example of a weak electrostatic interaction are two dipoles, right? So here, just to pick numbers, I picked two dipoles. The strength of each dipole is 1 to pi, and they're lined up and separated by 0.5 nanometers. So I've intentionally aligned the dipoles in one direction. That just makes it easy to evaluate that very complicated formula. When I work through the numbers, I end up with a value for the magnitude of U of R in this case is something on the order of a half KT, right? So it's much weaker. It's much weaker than thermal energies. And so that would mean that at room temperature, these two dipoles lined up in this way, separated by this distance, these two dipoles would be influenced by thermal fluctuations, right? Because thermal energies are on the order of the electrostatic interaction energy. Okay, so this is an example of a weak interaction. Okay, just two models. So now we have to worry about what the effect of thermal energy is between dipole-dipole interactions. They're weak. We've already decided they're weak, right? And we have to ask the question, how do we find out what the average interaction is if these dipoles are fluctuating due to thermal energies, right? And the answer is we have to do a statistical physics calculation, right? So we have to invoke Boltzmann statistics. And I just real quick summarize the essential feature of Boltzmann statistics. Boltzmann statistics says that there is a probability of finding a state of a system with energy epsilon sub r. So let's just imagine a system and let's say that its interaction energy is epsilon sub r, right? What's the probability that I would find that system at a temperature T, right? And Boltzmann says, well, that probability involves the exponential, evaluating the ratio of two exponentials. The numerator exponential is just e to the minus that energy, epsilon sub r, divided by kt. That's called the Boltzmann factor. And then I have to divide that by all the possible energies that the system can have access to. So I have to imagine that this parameter r spans all possible energies that the system can access. And I have to sum up the Boltzmann factors for all those possible energy states. If I divide that into the Boltzmann factor e to the minus epsilon r over kt, then if the system is in thermal equilibrium, that ratio tells me the probability that that state with energy epsilon r will be observed. Okay? Now that quantity in the denominator, if you've studied statistical physics, that's referred to as the partition function. And so you'll always find people in statistical physics trying to calculate that partition function for different systems, right? Because that's the hard thing. You got to know what that is. You got to know all the possible energy states to calculate the denominator, right? So there's just a whole raft of literature that describes how to calculate partition functions for different systems. But the thing you've got to recognize is this is a fundamental postulate of statistical mechanics, statistical physics, right? And it governs any system that's in thermal equilibrium. It's universal. Okay? Now, why is that important for this discussion? You'll ask. Well, if you have any quantity, y, let's say it's a dipole moment. Let's say y measures a dipole moment. Let's say you can have different dipole moments for a system. Each dipole moment is given us an index r. So we can have a whole raft of dipole moments, let's call them y sub r's. What is the average dipole moment that you would expect for a system that's in thermal equilibrium? Again, that's a question that's answered in statistical physics, and the answer is, right, you define a thermal average or an average value, so you can, the different books have different notation, so you can have this y bracket with a bra and a ket bracket, or you can have a y with a bar over it, right? That symbol means that you evaluate the probability that each state R can occur times the value of the parameter y of r at that state. Okay? So I don't care what y is. It can be an angle, it can be a probability of dipole moment, right? It can be any physical parameter y. Y can have any physical parameter as long as you can identify what energy it has for a specific configuration. You can then calculate the thermal average, the value that you're going to most likely see if you make lots of measurements of that parameter, right? And it's just given by this simple formula. So again, this is a problem of statistical physics, right? What does that got to do with our dipole-dipole interactions? Well, if these dipole-dipole interactions are so weak that thermal energies cause the dipoles to fluctuate and move about, then we have to calculate a thermal average of U. right? Now, how do we calculate a thermal average of U? Well, we have to calculate thermal averages of those cosine factors, because that's going to describe how the dipole is oriented in space. So if we want to do a thermal average of U, we have to do a thermal average of the cosine factors. The cosine factors are continuous. They're not discrete. We can't label them by an index R. So all the sums in the previous slide now have to be replaced by integrals. And we have to integrate over all possible configurations that these parameters theta 1, theta 2, and phi can have. So that's basically integrating over all solid angles. And so, for example, if you want to find the average value, the thermally average value of the cosine, okay, you have to evaluate the integral over all solid angles, cosine of theta, that's the physical parameter y in the previous slide, right, times e to the minus u over kt, where u is the interaction energy, and u contains theta. U contains theta, so that's a complicated calculation. You have to evaluate the numerator, you have to divide by the denominator, which is the partition function, and that then tells you the thermal average of cosine theta. Okay, a lot of work. Yes, sir.
So Ron, on the face of it, one might wonder why you've got cosines in the average order from theta, what those positives and negatives cancel out and you get a net zero. And maybe the answer, I'm just trying to think about this, is that there's a negative outside. So regardless how the dipoles are oriented, you always have negative potential energy. So it's going to be a non-zero average, even if you did not take the weighting given to it by the distribution function. It could be non-zero.
There'll certainly be a non-zero average because there'll be a slight preference for the dipoles to be aligned. So theta zero is.
So you're saying that it is the distribution is actually critical, because if it's evenly distributed, then it would be zero.
It would be zero. It's heavily weighted towards the lowest energy states. That's what that's what the Boltzmann factor is telling you, right? All these possible states that could exist with all different thetas. The ones that tend to be favored are the lowest energy ones. And the Boltzmann factor picks that out. And this is just the arithmetic that you have to do to crank it through, right? So I think you'll find that the sines average to zero, the cosines do not, because the cosines are even functions of theta, the sines are odd functions. I think that's what it works out. At the end of the day, right? Complicated calculation. At the end of the day, you find out something called the Keesom interaction, which is the thermal average of two dipoles, one with respect to another, separated by a distance r, as they fluctuate back and forth due to thermal energies. And that Keesom energy, right, doesn't look at all like the energy for two static dipoles, right? It's completely different. It's got a 1 over r to the 6th, it's got a 1 over kt, and then it's got factors in front that are related to the electrostatics of the problem. Okay, so Keesom solved this problem back in the early 1900s, doing this thermal averaging. And this is the interaction energy he got for two permanent dipoles that can fluctuate due to thermal energies. Okay, so that's. What is that? That, I think, is the fourth interaction we're talking about. The fifth interaction is a little bit more subtle, right? Each of these interactions get a little bit more complicated. So what I want you to think about is an atom or molecule that's placed in an electric field, right? Now, the atom or molecule, to begin with, has no dipole moment. But when you apply this uniform electric field, what's going to happen? You have to think about this physically. Well, the electric field is going to exert a force on positive charges that are going to repel the positive charges, right? Because positive charges always follow lines of electric field. That's the definition. So the positive charge will tend to move to the right. Any negative charges in that molecule will be attracted. they'll move in the opposite direction. Okay? So the negative charges will be offset from the positive charges by a small amount. And the net result is that there's an induced dipole moment now in that atom or molecule. So I've got a highly magnified view of the situation on the right-hand side of this slide. Right? The electronic charge cloud shifts one way, the nucleus shifts the other. In the process of shifting, you destroy the charge symmetry of the problem. You create a dipole moment P. That dipole moment P is called P induced. And what you find is that induced dipole moment is proportional to the strength of the electric field, and that proportionality factor is a parameter called alpha zero. So alpha zero is called the electronic polarizability of the atom or the molecule. And you can go to the web and you can look up values for alpha zero, right? They're just tables of these things. They've been measured, right? Alpha zero turns out, if you work through the detailed theory, alpha zero turns out to be proportional to the radius cubed of the atom or molecule, to a first approximation. The units are 4 pi epsilon naught, so very often you'll find values for alpha naught quoted in units of 4 pi epsilon naught. The units, the ratio of alpha naught over 4 pi epsilon zero has units of cubic meters, right? And so, for instance, just to give you a sense that this polarizability is related to the dimensions of a molecule, I look at the case of water, right? So for water, alpha over 4 pi epsilon naught is about 1.5 times 10 to the minus 30 meters cubed. If I take the cube root of that, I'll get an expression for R, capital R, would be then the radius, approximate radius of the water molecule. I get about 0.114 nanometers. If you look up in the tables what the radius of the real water molecule is, it's about 0.135 nanometers. So, right, the numbers aren't that terribly different, right? And the sense that you get from this is that the polarizabilities get bigger as the radius of the atom or the molecule increases. Right? So the bigger the atom or molecule is, the bigger R is, then the bigger the polarizabilities are. Right? So this is called the electronic polarizability. Why is this important? It's important because anytime you have a neutral molecule in an electric field, this will happen. You'll induce a polarization. You'll induce a dipole. Once you induce that dipole, then that dipole can start to interact with other molecules which also have induced dipoles, and then you start to get these induced dipole interactions. It's not permanent dipole moments only. Okay, so this is a complication. It's a subtle complication. What's the energetics? What's the energetics of this dipole in an applied electric field? The energetics are given by this simple formula, minus P dot E, right? So again, there's an angle cosine of theta, and this angle theta is going to tend towards zero if all things are equal, right? So if you put a dipole in an electric field, and if that dipole is free to rotate, theta will tend to zero to line up to give it, to make the energy as small as possible, right? Take advantage of the interaction potentials, right? So that's important because now, right, we have to ask what happens if you induce a dipole moment by an electric field, right? Right? The interaction energy is going to be this P times E times the cosine of theta. This dipole moment is free to fluctuate with thermal energies. So we're going to have to do this thermal averaging process again, right? And so if you calculate the thermal average of cosine theta weighted by this Boltzmann factor, you get this very famous Langevin function that was first derived in 1905, right? And that Langevin function can be approximated for small dipole moments with respect to kT, right? You can approximate that Langevin function by this factor 1 over 3 times the ratio of the dipole moment times the electric field divided by kT. And that all means, at the end of the day, that all means that you've got another contribution to the polarizability, right? Because you can write an equation for the thermally averaged dipole moment in terms of the applied electric field, in terms of another parameter alpha 1, and that parameter alpha 1 is temperature dependent. Okay? And that means that you can now write an expression for the polarizability of a molecule that's completely general. It involves this alpha 0, which is the intrinsic polarizability, how the charge separates under applied electric field, plus this thermally averaged function, which is due to the Langevin equation, right? And so this is the expression you get for the polarizability for an induced dipole moment, right? And you can put that into induced dipole, a dipole-induced dipole interaction, and you end up with something called the Debye interaction energy, right? It contains polarization, dipole moments squared. It contains polarizabilities, right? These are for two distinctly different molecules, P1 and P2, interacting with one another. The important thing is it's a 1 over r to the 6th, right? And all those other factors are often represented by a constant which we call C sub d, right? So this Debye interaction, which takes into account the interaction between a permanent dipole and an induced dipole, also gives a 1 over r to the 6th potential, electrostatic interaction potential, okay? And this is this interaction is always going on, right? At room temperature, you have a tip made out of atoms, you got a substrate made out of atoms. Substrate atoms, if they happen to have a dipole moment, can induce a dipole moment in a tip atom. And so therefore you've got a net attractive interaction between these two atoms that's given by Debye. Okay? Again, it's a very subtle effect. Was first calculated in the early 1900s, right? And I have one more that I have to touch on. It's referred to as the dispersion force. This is even more complicated. The dispersion force is an induced dipole interaction. Right? It's induced dipole. It depends on the ionization energies of the atoms or molecules that are interacting. Again, all the parameters that occur in that formula can be represented by a constant, which we call C sub L, right? Because London was the name of the guy who worked this out the first time. You also get a 1 over r to the 6th interaction potential. So I've gotten 3 1 over r to the 6th now, right? One is from dispersion, one is from Debye, and there's a dipole-dipole interaction, which is also 1 over r to the 6th, right? Just, if you don't know what ionization energies are, just a chart, ionization energies for the elements. It's a number between roughly 5 and 15 electron volts, right? So I think at the end of the day, I have to close up the lecture. At the end of the day, there are 3 important forces that are grouped into these things called van der Waals forces. There's this Keesom force, there's this Debye force, and there's this London force. Each one of those forces, or each one of those interactions, has a 1 over r to the 6th dependence. Right? And it depends on the molecules involved, which of those 3 terms is dominant. What's often done is that whole set of equations is written as a constant C divided by r to the 6th, and that is now the van der Waals force that's going to dominate, that's going to describe how 2 atoms or 2 molecules interact one with another when they're separated by a distance r. That constant C is going to be a parameter that we're going to try to evaluate. We'll start off with that in the next lecture. Show you some numbers that theorists have calculated. But this is sort of the end result of this lengthy discussion about electrostatic forces. All right. Since most materials are electrically neutral, all right, you cannot worry about charge-charge interactions. You cannot even worry about permanent dipole interactions. You have to start to worry about these fluctuating dipole interactions that govern an attractive force, that give rise to an attractive force between electrically neutral objects. All right. So I have to stop now. If you come back on Thursday, we'll pick up on this and show how you have to include this to accurately describe the attractive force between a tip and a substrate.